Hello, my name is McGuire Hodson, and this is my lab report for Lab 4, Oscillations. The purpose of this lab is to analyze the motion of a spring mass system oscillating in 2 dimensions and compare experimental data with a computational model. This lab is based upon Newton's second law of motion, which states that force is equal to mass times acceleration, as well as Hooke's law, which states that F spring equals negative Ks. The computational model simulates the motion of the mass based on equations of motion and plots this with the motion seen in Tracker. It also graphs the changes in the types of energy over time. The model demonstrated the predicted motion as exponential, but the actual motion as oscillating. The changes in energy were linear. The computational model includes the effect of gravity, Newton's second law, Hooke's law, and the conservation of energy. There are 3 main types of energy that are observed, which are gravitational potential energy, spring potential energy, and kinetic energy. The assumptions for the model are that the spring obeys Hooke's law, no external forces act on the mass, motion occurs in 2 dimensions, and that the mass is a point mass. The model is used to capture nonlinear motion and to visualize changes in kinetic energy, gravitational potential energy, spring potential energy, and total energy. So this first image shows Hooke's law, and the second animation shows Newton's second law. In this model, the system being analyzed is the mass attached to the spring itself, and the gravitational field of the Earth. The surroundings are the air around the mass and any external forces. For the model, the initial conditions are that the mass is 0.402 kilograms, the ball position vector is 0.857, negative 1.7140 meters, the ball does not have any velocity, the time is 0, the spring constant is 6.83, the relaxed length is 0.123 meters, and g is of course 9.8. In the model, a spring mass system is observed in the x and y dimension with the mass oscillating. Tracker is used to extract the position data of the mass in both the x and y directions. In the code, energy changes in the system are graphed, as well as the observed versus predicted motion in both the x and y direction. The energy changes are calculated using many formulas, and the momentum principle and Hooke's law are applied to update velocity and position periodically. So this is the relevant portion of the code. As you can see, many of the formulas used are included, and this is the experimental setup. So for both the x and y positions, the model predicted the motion as exponentially decreasing, but the experiment showed the motion to be oscillating. In the change in energy versus time graph, delta K and delta E increased over time, while delta U spring and delta U gravity decreased over time. The model predictions and data are likely different because of external forces and some incorrect modeling of the spring constant and relaxed length. So this is the first graph, shows the change in energy versus time. This shows the y position versus time, and this shows the x position versus time. So clearly there's a major difference in the expected motion versus the actual motion. For this model system, the energy principle is not satisfied. The total energy does increase over time, where it should be 0. This indicates some potential issues in the model. The oscillation period in the x direction is less than the oscillation period in the y direction, and it appears to be about 2 times less. This makes sense because it does not move nearly as much horizontally as vertically in the video. It also indicates that the spring is not symmetric and has some asymmetry in its motion. The model's prediction of motion varied significantly from the observed motion. This is due to a variety of possible sources of error, which include some incorrect model assumptions and incorrect initial parameter values. Additionally, outside forces may have affected the spring, such as air resistance and friction. So, despite the errors in the experiment, the tracker data did show the motion as oscillating, which was expected. Overall, this lab provided valuable insights into 2-dimensional motion, and it demonstrated the effectiveness of using computational models to predict the behavior of physical systems and to compare the predictions of the behavior of physical systems with data. And so that is the end of my video. Thank you guys for watching.